today I'm going to talk about very simple but powerful technique which is known as the Taylor series method of solving boundary value problems which arise from some real world problem. And I will be choosing in particular fluid flow instabilities problems in showing how a simple technique like Taylor series could be used in handling complicated problems, right? So the essence of Taylor series, I'll try to explain with the help of a transform technique, which people have named it as differential transform. Basically, it's a Taylor series solution. So it's the other name what we can give to this method. So Taylor series method or the differential transform method, which can be easily adopted to solve boundary eigenvalue problems. So that's the title of today's talk. And the outline is like this, and I will explain briefly about the mathematical problem that I've chosen from fluid flow instability, and I would highlight how Taylor series method or the differential transform method can be used in handling the boundary value problem arising from the said fluid flow problem. And once we obtain the solution by differential transform method, I would also highlight the accuracy and convergence analysis of the Taylor series, which will validate our results, and finally we'll come up with some conclusions of the study and further improvements on the proposed method. Okay, so that's the outline of my talk. So I'll start with a general 2-point boundary value problem, 2-point boundary eigenvalue problem, right? And you must be knowing such a boundary eigenvalue problem consists of the differential equation together with boundary conditions, and it becomes an eigenvalue problem due to the presence of the parameter lambda. You can see that in equation 1. And the solution of such a differential equation subject to the given boundary conditions will arise for, will be available only for some integral values of lambda, some integer values of lambda. And the solutions corresponding to those integer values of lambda are called as eigenfunctions, and the values of lambda for which the solution exists are known as the eigenvalue. And you can also bring in the weight function and change that weight function according to the problem on hand. And these problems in general are known as Sturm-Liouville problems in mathematics. And equations 2 and 3 represent general boundary conditions, and equations 2 are the left boundary conditions. There will be n minus, let's say there are r left boundary conditions, then there are n minus r right boundary conditions. And equation 1, which is a linear differential equation, together with equations 2 and 3 will give rise to boundary eigen value problem. And you should be knowing that the solutions of this boundary eigenvalue problem non-trivial solutions will exist only in the case when the differential equation is homogeneous and the boundary conditions are also homogeneous. So that's the condition has to see for the eigenvalue solutions. Okay, so the differential equation should be homogeneous, and also the boundary conditions should also be homogeneous. And given this scenario, the differential equations admit solutions for integer values of lambda, and those solutions corresponding to each integer value will be called as eigenfunctions. Okay, so this is a brief background of what is boundary eigenvalue problem. And where do we come across such boundary value problem in real world applications? So if you see the time independent Schrodinger's equation that we come across in quantum mechanics governs the wave function of a particular quantum system, give rise to a boundary eigenvalue problem. So I'll be using this abbreviation BVP, which stands for boundary eigenvalue problem. Okay, and the other places where BEVPs occur naturally are in the vibration analysis of mechanical structures, having several degrees of freedom. And here, the natural frequencies of vibration form eigenvalues, and the shape of vibrational modes form the eigenfunctions. And in the theory of elasticity and bending of beams, 2-point boundary value problems encountered abundantly. And in fluid mechanics too, instability problems of many fluid flows also give rise to 2-point boundary value problems, boundary eigenvalue problems. So with all this said, what we can remark at this point is, from the viewpoint of real-world applications, boundary eigenvalue problems are very important, and also the solutions for such problems are also equally prominent. So this presentation will highlight a simple but elegant technique which can be effectively used to solve such boundary eigenvalue problems subject to general boundary conditions arising in various applications. And in particular, as I told earlier, I'll be choosing a problem from the fluid flow instabilities in order to highlight the proposed method. Okay, so let's move on to the solution procedures that are available already. Remember, your boundary eigenvalue problem could be solved by using the methods which handle boundary value problems. So usual boundary value problems, whichever the method that handle boundary value problem, can be altered slightly in order to obtain solutions of boundary eigenvalue problem. Okay, so we'll just review what are the available methods for boundary value problems. So there are numerical methods such as finite difference method, shooting method, spectral method, which handle boundary value problems, and approximate analytical methods like homotopy analysis method, homotopy perturbation methods, which have been extensively used in recent past, and methods like variational iteration method, Adamian decomposition method, and the differential transform method, which I'll be presenting now, come under the category of approximate analytical methods. And all these, which handle boundary value problems, can be suitably altered to handle our boundary eigenvalue problems. All right. So I will show how this differential transform method, which is used for solving initial and boundary value problems, how that could be implemented for the case of boundary eigenvalue problem. All right. So with this brief introduction, I will just move on to the next item in the presentation, which is the mathematical formulation of the instability problem. Okay, so let me spend some time for those who are not from the fluid mechanics background, so that they can understand how this problem is arising and how we are going to handle that problem. Okay, so what I considered here is a Darcy-Brinkman convection problem in an enclosure. Okay, having sides at y equal to 0, y equal to h, and the lateral sides at x equal to minus L and x equal to plus L. So the origin is situated at the midpoint of the horizontal, lower horizontal line, lower horizontal plate, you could say. And the lower horizontal plate is maintained at a higher temperature, T0 plus delta T, and the upper horizontal plate is maintained at a lower temperature, T0. And the enclosure is filled with a sparsely packed porous medium, and the environments above the upper plate and below the upper plate are filled with tightly packed porous medium. So what does this do to this convection problem? So the presence of this tightly packed porous medium underneath and above the enclosure enables the heat and the fluid to be exchanged between the environment. Okay, so this mainly gives rise to what are called as general boundary condition. Remember, the aim of the presentation was to highlight the Taylor series method for boundary eigenvalue problem subject to general boundary condition. So in order to have a general boundary condition, such a problem is chosen. Okay, so that's the whole idea behind choosing this particular problem. So the system which is exchanging heat and fluid with the surroundings give rise to general boundary conditions. So that's the reason why it has been chosen this way. And you all know that whenever we model a fluid mechanics problem, so we have a set of equations. Equations 4, 5, and 6 are written in vectorial form, which govern these basic equations of fluid mechanics that are suitably written for the particular problem which is on hand. Okay, and in this equation 5 is kind of Newton's second law of motion in case of fluids. So the left-hand side represents the rate of change of momentum, and the right-hand side is the net forces acting on the fluid element. Okay, so the balance of the two gives the equation of motion for the fluid, which in general known as the Navier-Stokes equation. And equation 6 is known as the energy equation, and it comes from the conservation of energy. And equation 4 is the continuity equation, simplified for the incompressible fluid. So let me now move forward. I have told you briefly what are the symbols that are existing in this particular equation, and we need to know that the acceleration due to gravity is acting vertically downwards in the negative y direction. All right. So, okay, now coming to boundary conditions, since the upper horizontal boundary and the lower horizontal boundary are exchanging fluid with the surroundings, so the boundary conditions are modeled using what are called as Bevis-Joseph's condition. Okay, and this v equal to 0 is the condition due to there's no vertical through flow. Okay, so that is what V equal to 0 represents, and you can see that these two conditions are of the third kind, because both the derivatives and the variable are present, and you must be knowing that if you prescribe conditions only on the variable, it will be called as first kind conditions or the Dirichlet type conditions. And if you mention the normal derivatives at the boundaries, then that type of boundary condition is known as Neumann condition, or the second type boundary condition. When you have a linear combination of the two, it is known as the third kind boundary condition or the Robin boundary condition. And for the particular application that is chosen, both the velocity field and temperature field are governed by third kind boundary conditions at the boundaries, horizontal boundaries. And this makes the boundary eigenvalue problem little bit complicated. The third kind boundary conditions also can pose a kind of difficulty while getting the solution. So the conditions at the lateral walls are u equal to 0 and dou t by dou x equal to 0. And this is, one can put equations that I showed earlier using non-dimensional variables, which are given in equation 10. And once we use equation 10, we end up getting equations 11 to 16, and these equations are in the non-dimensional form. And here we are getting this ds, which is the slip Darcy number, all right, and we have the Biot number B, and we have the aspect ratio A, which is the ratio of length to breadth of the enclosure, and RA is the Rayleigh number. It is the Darcy-Rayleigh number, okay, and dA is the Darcy number, lambda is the Brinkman number or the viscosity ratio, VA is the Wada's number, M is the ratio of heat capacities. So these are the governing parameters that are appearing in the non-dimensional equations, and their definitions are given in this slide. So, okay, so we drop asterisks for simplicity and write the governing equation in this form, as shown in equation 17 to 22. And in component form, using stream function, I mean, not in the stream function, yeah, in component form, the equation 18, which is the equation of motion, the momentum equation, can be put into two equations, one in the x direction, one in the y direction. And so later we will eliminate pressure between these two equations and write a single equations for the velocities. And we also use on stream function, which will trivially satisfy our continuity equation. Okay, so it will reduce one equation and the number of variables by 1. So here the number of unknowns are u, v, t, all right, and p. By the application of stream function, so it will reduce the number of variables by 1. And we also eliminate pressure. So now the unknowns would be just u, v, and t. And since u and v are written in terms of the stream function psi, so there are only two unknowns now, psi and t. And the two equations for psi and t are given by equation 28 and 29. And remember, equation 28 is obtained by eliminating pressure from equations 24 and 25, and also using this stream function formulation given in 27. And equation 29 is obtained from equation 26, which is the energy equation. And corresponding boundary conditions can be put in terms of a stream function as given in equations 30 to 32. And Darcy-Rayleigh number acts as the eigenvalue for this particular problem, with solutions existing some particular values of Ra. Okay, so Ra acts as an eigenvalue for this particular problem. Now we perturb the system which is in the basic state, which is the quiescent state, and in the basic state the heat transport will be taking place in the form of conduction. And since the state is quiescent, the velocities are zero. There is no flow before the convection starts. Okay, and you can get the pressure in the basic state by using equation 25. Okay, so by balancing the pressure with the buoyancy term, okay, in the quiescent state. And yeah, we disturb this system by a small written as basic state stream function plus epsilon psi, and T is written as T naught plus epsilon theta, where epsilon is a small number which is known as the perturbation parameter, and psi and theta are the perturbations on stream function and the temperature respectively. And once you substitute equation 34 into equations 28 and 29 and drop the nonlinear terms in epsilon, so you get a linear differential equation. Okay, so this is known as the linear stability analysis. Okay, and this linear stability analysis give us information of when the convection sets in the system. Okay, based on the value of Rayleigh number. Okay, so equations 35 and 36 are linear in nature, and boundary conditions 35, 38, 39, if you see, they are homogeneous in nature. Okay, so after the perturbations that we introduce, so your equations are also turned into homogeneous linear differential equation, and the boundary conditions are also turned into homogeneous type. So as a result of this, give rise to what is called as boundary eigenvalue problem. And in this case, the physical parameter Ra, which is the Darcy-Rayleigh number, acts as the eigenvalue. Okay, and the corresponding solutions will be eigensolutions. And we see the time-independent solutions in the form of normal mode solutions as given in equation 40. And when we substitute equation 40, one gets equation 40 into these equations, 35 to 39. One gets solutions, equations 41, 42, 43, and 44. And the B square, which appear here in these equations, are the wave number. Okay, and one could set, they consider disturbances both in the horizontal direction and the longitudinal directions, and one can also set A to 0 to make the problem simpler. Okay, which is the longitudinal wave number, and we set A to 0 for further analysis. All right. So this is the boundary value problem. Finally, boundary eigenvalue problem. Finally, one obtains from the instability of Darcy-Brinkmann convection problem. So you see it's a fourth order differential equation in Fn and second order differential equation in Gn, and you have the 6 boundary conditions satisfying, subject to those two differential equations. And Ra is going to act as a eigenvalue. And therefore, the solutions here are written as F subscript n and G subscript n, so which will correspond to corresponding eigenvalue Ra, which are integral multiples of R. So one can take the basic state normal mode, basic state solution. I should not say basic state, fundamental mode of solution. Okay, so the fundamental mode n equal to 1, and we will know that the system will be, if the system is unstable to fundamental mode, then it will be unstable to rest of the modes. So we don't have to consider all the modes. So we'll set n equal to 1 further. Okay, and now comes to the Taylor series method. So the basic ideas were given by Pukov, which is a Russian mathematician come electrical engineer, in the year 1982, while solving circuit problems, the linear circuits and the nonlinear circuits. When he was designing those things, so he come up with an idea of differential transform, which is basically Taylor series. I will explain what is differential transform method. Is one of the transform method. So many of you who work in the engineering discipline or mathematics department will know what is the strength of a transform technique. So a transform technique always converts a problem which is relatively difficult into a problem which can be handled easily. So any transform method has been devised in such a way that it converts a difficult problem into an easier one. So differential transform belong to one of those category of transform methods. Okay. And you must have come across transform methods like Laplace transforms, Fourier transforms, Z transforms, fast Fourier transforms, so on and so forth. Here, differential transform does not belong to the category of integral transforms, but it is kind of a differential transform. Okay, and the whole idea of this differential transform arises from the Taylor series. So that's why in the title I have given the title as Taylor series solution. Okay, so the words differential transform and the Taylor series go synonymously. You can use them interchangeably. Okay, and what is the main use of this differential transform? So the main advantage of this the differential transform is it could be used on nonlinear differential equations. That's the strength of the differential transform method. And it does not require any linearization or the discretization or the presence of any small parameters. Okay. Another important advantage is that it reduces the computational work drastically, yet giving us very accurate results. Okay, and it also has a fast convergence rate. I will illustrate this aspect in some time. And the differential transform method is also free from discretization errors and gives very good approximation to the closed form solutions, if at all the closed form solution was available. Okay, and it's a semi-analytical, semi-numerical method. Yeah, I think this is a repetition of what I said earlier. So it does not require any presence of any small parameters. Okay, and the mathematical definition of differential transform is it goes as equations 46 and 47. And if you see the kth order differential transform of a function u of x is defined as u of k, which is equals to 1 by k factorial kth derivative of u evaluated at the point x equals to x naught. And if you see closely, this is nothing but the differential, Taylor coefficient in the Taylor series, okay? The coefficient of the term x minus x naught whole power k. And that Taylor coefficient is taken to be the differential transform of the function u of x. And the inverse differential transform is defined as so u of x equals to u of k into x minus x naught whole square. And if you see equation 47 with uk being the Taylor's Taylor coefficient, it's nothing but the Taylor series expansion of u of x. So you must be thinking that I'm cheating you by calling this as a transform technique. It's just a Taylor series, to be honest. Yeah, so the answer is yes, it is a Taylor series, but I'm introducing this differential transform just to switch over from the x domain to k domain, okay? So essentially 46 and 47 are from the Taylor series, all right? So there are some properties of this transform. By using definition 46, you can derive a lot of properties of this differential transform. So I list a few properties which will be used for the present study, okay? So property number 1 and 2 are the linearity property of the differential transform. And the linearity property of differential transform is inherited from the linearity of the derivative operator. Okay, since the derivative operator is linear, your differential transform also becomes linear. So properties 1 and 2 are linearity properties. And property 3, if the function u is written as a product of two functions, v and w, then the transform of u is given by the summation, okay? So this is one of the important property which will be used to handle algebraic nonlinearity, okay? So the algebraic nonlinearity can be handled using property number 3. And property number 4 is the differential transform of derivative. So if you have a mth order derivative, then the differential transform is given by this particular equation. And this is for the partial derivative. So you can ignore this particular property as it relates to what I'm presenting. So the properties 1 to 4 are the ones which are used in the present solution procedure. And all those properties can be derived by using equation 46, okay? Now let us see how we are going to handle the boundary eigenvalue problem using differential transform method. So the differential transform method in its original form can be applied to initial value problems, all right? So there is a need that we convert our boundary eigenvalue problem into an initial value problem just to facilitate the use of differential transform method, okay? So for that reason, what we do is we convert the given boundary eigenvalue problem into initial value problem. Before that, you must recall that RA is an unknown here. So your RA also needs to be evaluated or found as a part of the solution procedure. So there are already two variables, Fn and Gn. And if I introduce this as the additional variable, so there are three variables. And we are introducing this as an artificial variable. So if I mean, not the artificial variable, extra variable. So if I introduce an extra variable, so for closure, I would require one more boundary condition. All right. So there are three variables now, f, g, and ra, but only two equations. So I need to introduce an additional differential equation in order to meet closure, and I would also require an additional condition for that particular additional variable. So how it is done is using this particular way. So we know that the eigen functions are can be normalized, because any scalar multiple of an eigenfunction is also an eigenfunction. So if we use a normalization condition, that will cover up one additional boundary condition, and I have not shown the additional differential equation explicitly anywhere, but this is the last equation which I'm using, which I'm introducing as an additional differential equation. Okay, and remember, f is of fourth order and g is of second order, and that can be put into a system of 4 plus 2, 6 first order differential equations. Okay, and the seventh equation is an artificial equation where u7 is the Rayleigh number, and I'm just saying derivative of Rayleigh number is 0. That is obvious because Rayleigh number is a constant. So the last equation is kind of an artificial equation introduced for the problem of closure. Okay, and the corresponding boundary conditions are being converted by using what are called as missing initial conditions. Okay, so u20 is not prescribed, so I'm assuming it as alpha star, and similarly u40 is also being assumed as beta star. Remember, u1 is the variable f, u2 is the first derivative, u3 is the second derivative of f, and so on, and u5 is the variable theta, and u6 is the first derivative of theta, and u7 is the Rayleigh number. Okay, and yeah, so Ra is also an unknown, beta star is also an unknown, alpha star is also an unknown. So the given boundary eigenvalue problem is being converted into an initial value problem. Now, this is the suitable equation on which we can apply the differential transform to get the series solution. And if you observe this equation, there is a u5, u7 term present. u5 represents theta, u7 represents Ra. So since we are dealing Ra as an additional variable, so this could be treated as a nonlinear term, and this nonlinear term will be handled by property number 3, which I presented earlier. All right, and there's some more assumptions made that we set value of lambda and m to be equal to 1 to minimize the number of parameters. Okay, and this conversion of given boundary eigenvalue problem into an initial value problem is somewhat similar to the technique of shooting method. Okay, there also we do the same thing. We convert the boundary value problem to an initial value problem. Okay, and all right, so once we apply a differential transform onto various equations in in system 50, you end up getting the equations being transformed into from y domain to k domain. Okay, and here we have used property number 4 to handle those derivatives, and for handling nonlinearity we have used property number 3, and you see this summation comes in place of that nonlinear. All right, so these are the 7 recurrence relations which we obtain after the application of recurrence relation. And as I mentioned earlier, this recurrence relation is giving you the Taylor coefficients. So once you have these Taylor coefficients, with the first few Taylor coefficients being evaluated from the initial conditions, you can write down the Taylor series by using one of the equations that I presented earlier, by using this equation, which is the Taylor series. Okay, so yeah, so your eigen functions are obtained using equations 52 and 53. And remember, your solution is kind of an infinite series in Y. And this infinite series is supposed to converge for a particular value of Y, which is called as the radius of convergence. And since the problem is a 2-point boundary value problem and the value of Y is in between 0 and 1, so you don't have to really worry about the radius of convergence. Okay, so it is in that band 0 to 1, so which will be converging for all values of Y in the interval 0 to 1. And all you need to do is just to see how these partial sums converge. So before I go to the partial sums, I'll just show one result where the Rayleigh number is plotted as a function of number of terms of the series. Okay, for the two cases, stress-free isothermal case and the rigid isothermal case. And in both the cases, if you see the number of terms, when you reach number of terms as 12, the Rayleigh number gives a constant value. So for the rigid case, it is around 3,400 something, and for the free boundaries, it is around 1,000. Okay, so you see the value of the eigen value, the eigenvalue RA reaches a constant value, which indicates that about 12 to 13 terms are enough to achieve the convergence. Okay, and so this is one figure which indicates that our method converges with less than 20 terms in the series. Okay, now these are the partial sums which are plotted. These are eigen functions with various so if you take first 4 terms of the series, you have this solution. 6 terms of the series, you have another solution. And if you see, the solutions are converging to this parabolic profile. So you see only up to 20 to 22 terms are enough to achieve the convergence. And the rest of the figures also show the partial sums plotted for various values of number of terms of the series. And they all show that the result converges in less than 20 terms. And we have also compared the solution of solution obtained by differential transform method with that of the boundary BVP4C, which is a MATLAB inbuilt routine. And you see there is a close agreement between the values that we have obtained using Taylor series method and the MATLAB built-in routine. So which also tells us about the accuracy of the present method. Okay, so the present method is accurate enough to give our eigenvalue. And that was done for shown for different values of Biot number, and this table shows the Rayleigh number for different values of Darcy number. All right, so even in this case, you see that the results are matching very nice. But the whole idea of today's talk was to highlight how a simple technique like differential transform could be used effectively in handling complicated problems arising from real-world applications. And I'm going to conclude today's talk by mentioning salient features of differential transform method. And as you have all seen, that it has good accuracy and convergence, and with less than 20 terms needing for the convergence. And you can further improve on the convergence using payday approximation, and the results are concurring with the BVP 4C routine results, validating the present one. And external convection has a destabilizing effect, and partial slip has a stabilizing effect. These are important from the fluid mechanics point of view. But what is important from the mathematics point of view are the first two conclusions. And as I mentioned, one can study the uniform convergence theoretically, and you can devise methods which help increase your convergence. Yeah, so these are some of the references. I think I'll end at this point.